the angular distribution of the radiated intensity due to an arbitrarily moving point charge. And what we got was one minus ER dot beta plus 2 beta dot ER dot beta dot divided by, sorry, this was to the power of 4, not 2. One minus ER dot beta to the power of 5 minus ER dot beta dot squared divided by gamma squared this home so I suppose there's no question about this. And we also, as part of the home assignment, you had special cases. Now, non-energy there's not much I can do about it. Can you hear me now? Is it better?
No, sir, it's cracking. We cannot follow you. Means your half of the voice is cracking.
Okay.
We cannot hear you, sir.
Yeah,
Yes.
so there was a little problem with the internet. Okay, so I'm audible now, right? Yeah. See, this is beyond my control. It's Airtel which is controlling it. I have an Airtel hotspot, and whatever they do at the Airtel tower is beyond my control. I'm so sorry. But you can hear me now, right? Ritesh, can you hear me? Yeah, can you hear me?
So your voice is still cracking a lot.
Let me try to fix it. So what does non-relativistic limit mean? Non-relativistic limit, as you know, means that beta becomes very, very small. Beta goes to 0 and gamma goes to 1. So this is a limiting situation. We don't take exact values here, but whatever is smooth as beta goes to 0, you can set to 0. So in that case, we have di rad t omega non-relativistic. So this is equal to q squared by 4 pi c beta dot squared minus dr dot beta squared. And the reason we are able to write it is because the denominator in this limit reduces to 1, gamma goes to 1. This term drops out because there's beta dot. This term drops out because it's explicitly linear in beta, okay? So we just have these two terms, and that's this. And this you can write, of course, as q squared by 4 pi c beta dot squared can be taken out. And this is 1 minus cosine of the angle between ER and the direction. So this is beta dot. Okay, from this term, is beta dot. So cosine of the angle between ER, so this is sine squared of the angle between ER and beta dot. Okay, so that's the expression we have. Q squared beta dot squared sine squared theta. So for a particle, a charge which is moving slowly so that the non-relativistic limit can be applied, we see that the angular distribution of the radiation, there's still acceleration, of course, because beta dot is the acceleration. This is exactly dv dt 1 over c dv dt whole squared, right? So that's a standard acceleration by c squared. And we have this sine squared theta dependence. So now if you ask, so if this is, we can visualize a situation if we imagine that the velocity and acceleration are parallel. For instance, if the particle started off with an electric field behind it, so velocity and acceleration are parallel. So this is the direction of the velocity and acceleration because they are parallel. And this is the direction of r, ER. And that's the theta we are talking about. So now if the particle is going in that direction, so we have a particle, let me draw the picture better. This is the particle moving in that direction. And it is accelerating. Therefore, it is radiating. And this is the angular distribution of the radiated intensity. What direction do you believe the radiation would be a maximum? Okay, now that's very easy to answer because the only dependence on the angle is here. And you can see then that if you look at various directions, let's say from this point you look at various directions, then of course the maximum is when theta is pi by 2. So this is, you see, this is quite interesting because it's just the opposite. So I'm drawing the radiation lobes on both sides. Okay, just like I did for the ultra-relativistic particle. Now, in the case of the ultra-relativistic particle, what we had was this. This was the direction of motion, and then we had lobes like this, right? So directions very, very close. Well, my drawing is very bad, but never mind that. So these two directions had the maximum radiation. So this was the direction of beta. Here, on the other hand, it is this direction. So for non-relativistic particles, the radiation is maximum at an angle of maximum radiation for theta equal to pi by 2. Okay, so this is the ultra-relativistic UR, and this is the non-relativistic. Then I get a radiation lobe which looks exactly like this. So the case when they are parallel is very well suited to discuss the angular distribution. It is also true that if you discuss the parallel case rather than the perpendicular case, we will discuss the perpendicular case a little bit later, but in the parallel case, you see, the advantage is that some part of the angular distribution even here, well, in the special case for the parallel situation, beta parallel to beta dot, the angular integration is easier to do. Okay? And it's done somewhere in some books. I think Landau is done. So here we find that now, if I ask for the total intensity of radiation, which remember is dE dt, right? The power radiated is what? Power and intensity we are using synonymously. So power radiated, I can actually write this down explicitly because this is q squared, beta dot squared by 4 pi c integral d omega sine squared theta. Theta being the angle between the direction of the line of sight from the charge to the observer and the direction of motion of the charge, okay, the direction of acceleration of the charge. So I should really say that this is the direction of acceleration. But you realize that in the parallel case, it's much easier to do the physical comparison. So for purpose of physical comparison, that is better. Right, so D, I should say that here. So that's this. And we can now do the integral, right? It's easy to do the integral. So it's q squared beta dot squared divided by 4 pi c. But you see, there is no phi dependence in the integrand. And what we get then is a 2 pi, which cancels this. So we get 2c, 0 to pi. D omega has a d theta sine theta. So I get this sine theta sine theta, and I write the sine squared theta as 1 minus cos squared theta. Okay, and what I get from here is just a factor of 2/3. So this is a trivial integral. So this is, well, 4/3. I get 4/3 from here. The integral gives me a factor of 4/3. So the answer is 2 by 3 q squared by c beta dot squared. So you see, in the non-relativistic example, we can actually calculate, right? We can calculate the total intensity of radiation by integrating over all angles. We couldn't do that in that other case. This integral is very hard to do. It's almost impossible to do, except in special cases. And one of the special cases in which you can do the integral is a non-relativistic example. Okay? So this formula, by the way, has a name. It's French physicist. So this radiator, so let me write it again. I rad. Well, I can write it in another way. Q squared I c cubed, acceleration non-relativistic squared, right? So this formula is called Larmor's formula. And it's there in every textbook. Every, well, graduate level textbook which discusses radiation. But there are certain nice things about this formula, which of course does not appear in the full relativistic formula. And I'm going to tell you about that now. See here, you can write this as 2 by 3, right? C cubed d by dt d squared by dt squared. Well, hang on. Put a bracket here, a square bracket. D squared qx bar. That's the trajectory of the particle, which is a function of time. Okay, so you might ask, why are you writing it in such a weird way? But this is true, isn't it? This is equal to that, right? I don't think there's any objection to that. I've simply put q inside, and this d2 dt squared, of course, does not act on q. It acts on this, gives me the acceleration, and that's a square. So there's no problem with that, right? So this formula is here. But the reason I've written it like this is because this quantity has a physical meaning. It is the dipole moment. Oh, sorry. P. It's a dipole moment of a time dependent, of a charge which is moving in a time dependent way. Okay. Usually you might think of a dipole moment as, okay, so let's say a little bit about the dipole moment here. Usually the dipole moment of a static distribution, right? You know what that is. That's the dipole moment of a static distribution. And for the case of the usual case of discrete charges, this is nothing but sum over I. If you have a bunch of charges located at various coordinates xi, then that's what the dipole moment is, right? Now, it is from this formula, so if you have x bar, which is the trajectory of the particle, then at every instant we have an x bar. So what we can imagine is that there's like a conglomerate. If you take the entire system, over all time, then this is like an association of particles. Okay, and that is why qx is the dipole moment. Of course, the dipole moment here is a function of time. Okay, so what we have is a very strong formula. This is the strength of Larmor's formula. And that strength is the following, that I rad, the power radiated, is 2 by 3 q squared by c cubed. P, the dipole moment, second derivative squared. Okay, so what we're saying is, although it's a single point charge, suddenly the whole thing generalizes We started off with an arbitrarily moving single point charge and we calculated the power radiated by it. But what we get instead is a system where we have any object, any distribution of charges with a dipole moment which depends on time such that the second derivative is non-zero will cause radiation. Okay? Will cause radiation. So this is a generalization from particle
They say you're good at chess.
to
We
a
should play.
to charge distribution. This is not something we could have done in the relativistic way, but it's something which happens in the non-relativistic approximation. So in the non-relativistic approximation, radiation in electromagnetism is always through the dipole. Now this carries over to the relativistic situation, but in the relativistic situation, we will have higher order multiples. So this is an electric dipole. So this is, remember that this is E1, it's called E1, which is electric dipole. But this is just the first term. Remember that in the non-relativistic approximation which we did, right, we took beta small limit, which means that this is the first term in that expansion. So there will be other terms proportional to the velocity because we ignored all terms proportional to velocity. Obviously, there will be terms which will be in higher and higher powers of the velocity, or what is the same, higher and higher powers of beta, which is V over C. So you expect that there will be a series. In fact, you can work out the terms from here in that expansion, right? And when you do that, you know that within this formula also, although it was not obvious to us, within this formula also, there's an entire series which looks like radiation due to a distribution. The first term in that series is the electric dipole. The next term will be magnetic dipole. Then we should have electric quadrupole, magnetic quadrupole, and so on and so forth. Of course, what these things mean, we will talk about later. Because remember that there is a little difference. Okay, so there is a little difference. Oops, I meant is to go to the next page. Sorry. The difference is the following. See, your intuition about dipoles and quadrupoles, etc., will usually come from electrostatics. Now, in the electrostatic situation, what you know for sure is that the potential, the scalar potential, also goes down for the contribution from higher and higher multipoles. So the dipole has a higher contribution than the monopole. The monopole is just a charge, which has a 1 over r. The potential for a dipole in electrostatics goes as 1 over r squared. The potential for a quadrupole distribution goes as 1 over r cubed, and so on. So it's a 1 over r expansion as well, right, as you do the expansion in multiples. However, that will not work in this case. Here, because we are dealing with radiation multiples, we'll talk about this a little more detail, hopefully tomorrow, in the next week's lecture. I shall have a lecture on multiple radiation. But you see here, on the other hand, each potential, and we have two potentials now, the scalar potential and the vector potential, each of them for all multipoles will only go as 1 over r, because that's only the radiation that one can observe. So unlike static multipoles, radiation multipoles have a different behavior with regard to dependence on the spatial coordinates. Okay, that is something to remember. Okay, now here as well, we know that the potential, we worked out the potential. Everything has been worked out, and the potential goes as 1 over r The radiation fields, the electric and magnetic fields go as 1 over r. Those are the radiation, electric and magnetic fields. So everything goes as 1 over r, because if they didn't go as 1 over r, we wouldn't see them. We wouldn't see light from a star. However slowly it may be moving, we will not see it. On the other hand, giving it a dipole means that there is no, so this is the most important lesson of electrodynamics, is no monopole radiation in Maxwell electrodynamics. Okay? Now, this is something that you have to remember. You have to understand. You have to think about it. Okay? There is no monopole radiation. Now, what do I mean by monopole radiation? For instance, let us think of an example. So let us think of a sphere. Let's say uniform sphere full of charge. So the total charge is Q, right? Well, it's uniform density. It's not Q. What I want to say is that charge density is uniform. So rho equal to constant. Well, it's not necessarily a constant. What I would like to say is it's not that it's a constant. Let's say that this is a function of mod x alone and also time. So one way of thinking about it is to take a fixed amount of charge, right, and put it in a volume, but the volume is changing with regard to time. So the volume, let's say, is going up and down. And rho is spherically symmetric. But it's so the spherical so this distribution is always at every instant of time, it's spherically symmetric. Okay? So let me just turn on my camera for a second and show you what we are imagining. What we are imagining is something that is like a balloon, right, which is oscillating. The balloon is full of charge. Okay, it need not be uniform. It could be spherically symmetric. Okay. Now, one way of thinking about it is that all these charges inside this balloon, okay, of course they're accelerating, right? So, of course, we always define the dipole moment in the same way, right? X. So what is it equal to? Anyone? What is the dipole moment in this case equal to? There should be a way of answering this without having to do a huge calculation. You can do it by a huge calculation. I'm not giving you the actual dependence, but you should still be able to answer me. Let's see. This is an old question, so it's like a quiz. Can anyone tell me what the dipole moment is? Hello? Maybe Shrestha? Yeah, Shrestha, can you tell me what the dipole moment is? Hang on, just one sec. I want to ask Shrestha. What is the dipole moment in this case? Shrestha, are you there, madam?
Yes, sir. Yes, sir.
So what is the dipole moment in this case? If this is spherically symmetric, then what is the dipole moment? Okay,
So
somebody else? Yeah, go ahead.
Is it linear in the x term?
You have to tell me, ma'am. You can't answer a question by asking a question. That is usually not the case, so you have to answer. Someone else wants to answer? Okay, Shafaq.
So
Hello,
I'll take a
Shafaq.
minute to think about it.
Okay, somebody else wanted to answer. Is it Rishabh? Rishabh, you wanted to answer? Rishabh? No. Rishabh has a problem with audio. What about Ritesh? Ritesh, you want to answer? What is the dipole moment in this case? Anyone else wants to answer?
Sir, 4 pi integral rho x into x cube into
That
dx.
is, I'm sorry, Akshay, that is not the correct answer.
But you don't know, I don't know that rho of the system.
That is the whole trick. That is the whole trick. But I told you that it's spherically symmetric.
Therefore, I said that I removed that 4 pi term.
That doesn't help. You still got the wrong answer. Anyone else? This is the third time I've used the word spherical symmetry. So it looks like.
Sir, okay, I
Yes.
just wanted to
Yes.
try once. So the row, you said that it's symmetric, right? So it is.
Spherically symmetric. Yes,
Yeah.
ma'am.
So row of minus
4
x
pi
equal
cube.
to row of x. While if you change the sign for x, it is antisymmetric in sign. So the product should give you 0.
Yes, your reasoning is not right, but your answer is absolutely right. Reasoning is not quite right. Let me tell you why. You almost got it right, Shafaq. It's a very simple thing. You see, this is a vector, which of course is a function of time, but it's a vector, right? Now, if you're spherically symmetric, you see, if it's spherically symmetric, what direction of vector? What direction will this vector have? Because every direction is equivalent to every other direction, which is extension of what Shafaq is arguing. For every x, there's a minus x. Yes, but that is true for every x, every minus x. And therefore, simply by rotational symmetry, I cannot get an answer. Because P of t must have a direction. And there is no admissible direction because every direction is compensated by the opposite direction, which is what Shafaq is saying in her own way. But the answer is absolutely right. Now, those of you who are unconvinced, you do the following. You actually remember there's an x, and this is the trick here, the x. So you have d cube x, there's an angular dependence here, but there's also x. X has the x component, the y component, the z component, which can be written in terms of the mod x and also the angles. So the mod x simply goes for the right, and that's why this dependence on mod x is irrelevant. But if you do the integration over theta and phi, you will get 0. It is a question of direction, not magnitude. All of you were focusing on the magnitude of this vector. Magnitude can be 420. I don't care what the magnitude is. But there cannot be a direction due to rotational symmetry. The symmetry excludes any possible direction in space. Now, this is an argument which you have to think about. And as I said, those of you who are unconvinced by this argument are welcome to try out the calculation. Write x equal to, do it the old way, x equal to I times x cosine theta, etc., etc. Do all that. So what I'm saying is you write x equal to ex, x plus, ey, y plus ezz. And then express x, y, z in spherical polar coordinates, theta, r theta, x theta, mod x theta phi, and then do the theta phi integral, you get 0. Okay? And that is because it's a theta phi, not mod x. The mod x decides the magnitude. It's the theta phi which determines the direction. And if there is no possible direction, because the fact that you are integrating over all possible directions, and all these directions are therefore equivalent, and therefore P of t cannot be sustained by a spherically symmetric distribution. Now, this is reminding you of an old result in electrostatics, which you should have remembered now that you've done so much of electrodynamics. You should remember that a spherically symmetric charge distribution, whether time dependent or not, cannot have a dipole moment. And therefore, in my example, where I have a balloon which is being inflated and deflated, full of charge, but spherically symmetrically organized, then P of t must be 0, and there cannot be any radiation. Okay? Although, if you look into the balloon, each charge is accelerating. This is something extremely weird, right? Now, just to emphasize this, let me go on to another example. So this is example 1. And this is another example 2, which simply emphasizes this point. So, ladies and gentlemen, friends, the fact that a spherically charged distribution cannot have any multiple moments can also be viewed from another point of view. Look at the sphere. The sphere, if you have a sphere which has a charge, then of course the charge density in electrostatics, the charge density is spherically symmetric, right? Now, if it's spherically symmetric, from Gauss's law, you know that the electric field outside the charge is as if the entire charge contained in the distribution was concentrated at the center. Okay? So that's like saying the electric field due to this distribution at every instant of time only sees this entire charge, the volume integral of this rho, concentrated at the center. This you know already from Gauss's law. Gauss's law works for electrodynamics, not just for electrostatics. So we know from Gauss's law that for a spherically charged distribution, the entire charge is concentrated at the center. In that case, if this charge is a function of time, for whatever reason, there is no monopole radiation. And because there is no monopole radiation, even if you have a charge somewhere sitting, but the charge magnitude changes as a function of time, this does not radiate in Maxwell electrodynamics. Okay? So this will not radiate in Maxwell electrodynamics, and this is one of the key features of electromagnetic radiation. And it is this feature which requires possible. Nature has ruled it out, so we need long things, antennas, to capture radiation. This is all very related, it's all very practical. It's all very practical. So it's not no longer in the realm of pure theory. It's absolutely in the realm of engineering. It's gone away from theory to engineering 50 years ago. Okay, before I began my studies in electronics, this was there already. But we are doing theoretical physics, and therefore our point of view is just to emphasize that there is no monopole radiation in Maxwell electrodynamics. You see, this is different. This is different from the radiation due to a scalar field. A scalar field also radiates. A scalar field also radiates. Radiation simply means energy being transmitted from the source to the outside world. So just like there is electromagnetic radiation due to a point charge, so also there could be a scalar field due to a point into a monopole. But a scalar field will radiate in the monopole, but not electromagnetic fields. Okay? So we must have dipole radiation as the lowest order multipole. There is no monopole radiation. And I'm going to underline this no, so that it gets ingrained in your understanding that there's no such thing as monopole radiation. Now, if you are asked to show quickly why is there no monopole radiation in Maxwell electrodynamics, what we have discussed today is a nice, sweet way of showing it. A nice, beautiful way of showing it. That the leading order in the non-relativistic limit is the electric dipole. Okay? But there will be corrections to that, as I described, because in the non-relativistic limit, you always, in any limit you take, you can always make an expansion in that limit, especially because the limit is in small beta. You can make an expansion in powers of beta. And indeed, each power of beta is called a higher order multiple, right? And we shall have a little bit of discussion later on to show that. Not today, but some other time. Okay. Now, to carry on, as I said, I wanted to give you another example. So let us think of a bunch of charges, right? A bunch of charges. So P, as I wrote down, P is the sum of these charges. That's the definition of a bunch of discrete charges located at xi from the origin, looked at afar. By the way, you know that the multipoles are always looked at from very far away. And as you come nearer and nearer, higher order multipoles get generated. That is a standard law in electrostatics. So P is Qi xi. Now I want to write it in the following way. I want to write it like this. Qi, let's say the mass of each charge is Mi. Okay, and now I'm going to make an assumption, right, that Qi by Mi is the same for every I. This ratio, charge by mass, is the same for every I. So let's call that Q by M. That ratio. This ratio is Q by M. Not that every charge is Q, every mass is M. That would be a very restricted case. But when this ratio is the same for every I, we can call it Q by M. But then I can call this I Mi. Okay. Now, this quantity here, this you can rewrite in terms of the capital M, the total mass of the system of charges, times the x corresponding to the center of mass. That's indeed the definition of the center of mass, right? Okay? So what we have shown is that P is this ratio Q by M, which is the common ratio Qi by Mi for all the charges, times the total mass of the system times the coordinate of this. So that if we want to know now P double dot, that is clearly Q by M times the mass times the acceleration of the center of mass. Now, if it turns out, if the system of charges has no force acting on it from outside, then this is zero. When no force from outside. No external force. Isn't that right? If the center of mass has zero acceleration when there is no external force. Okay, so in the case that you have no external force, as in this situation, there was no external force, everything was internal, then the dipole moment second derivative is zero. Of course, this is not zero, Here I took an exceptionally restricted distribution, which is spherically symmetric, but you can generalize this to the situation where the dipole moment is still not zero. However, the dipole moment, the second derivative of the dipole moment is zero because this has no acceleration. So this means again, this is a more general case that there is no radiated electromagnetic power. Okay, so this non-relativistic limit is quite rich, but it has restrictions and it tells us what kind of charge systems. Now, we are, of course, talking about charge systems. It tells us what kind of charge systems do allow radiation to happen. Okay, so that is why it is of great importance. Okay, now I want to continue this discussion and talk about spectral representation. Now, by spectral representation, what we mean is or spectral distribution. Thank you. Spectral distribution of the radiated energy. So what we have here so far is IRAD, the Larmor formula, which remember is dE rad dt, and that is equal to 2 by 3, right? Yeah, so 2 by 3 c cubed, right? So that's the Larmor formula. So that's the power radiated. But what we want to know is this. How much energy is radiated between frequencies omega and omega plus d omega? That's what we'd like to know. Okay? So instead of talking about it in the time domain, we are asking the question in the frequency domain. Now we know the time domain and frequency domain are related by, right, by Fourier transform. So use the method of Fourier transforms. So if you have a function in the time domain, then this is given in terms of the frequency domain. Or of course, minus infinity, everything is supposed to be well defined over the entire real line. So that's supposed to be the Fourier transform of this guy. And you also know this is the inverse transform, and you also know the actual transform f tilde of omega is dt e to the I omega t ft, right? So this is all well known. But from here, we can deduce a formula. F squared of t is equal to Can anyone tell me what this formula is called? What is the name of this formula?
Total cross section?
No. Where cross section? We are not even discussing scattering, sir. It's a mathematical
like-
formula.
I guess.
Sorry, come again. So tell me what this formula is. Well, it goes by a person's name. So let me remind you, you have seen this formula many times. Parseval's formula. Have you not seen this? Have you not seen this in quantum mechanics or, you know, Fourier transform theory? Have you not seen this? Hello?
No, sir. I mean, I can't recall seeing this.
You have not seen this.
Sir,
Okay.
from
Yeah.
BSc course, I recall the Parseval's theorem.
Yeah, this is the same. Formula theorem is the
Yes,
same.
yes, yes.
You recall Parseval's theorem, but who is this? Let me see. Who's answering? Shafaq says she doesn't remember, but who is Aditya says he remembers. But what about the others?
So
What about the other?
I did it in Fourier series.
Fourier series. Well,
Yeah.
if you know how to generalize that to Fourier transforms? In other words, do I have to prove it? Do I have to prove it? That's the question I'm asking. It looks like I have, right? Okay, I'll prove it. I was not going to, but let me try to prove it. The proof is not very difficult. So I have to recall the proof now, because I thought everybody knew this. So f squared of t, right? So we write this as f of t times well, there's no need to do it twice. Whenever I try to write fast, this pen revolts. Sorry, I made a mistake. Let me go back and correct the mistake. I think it is this. I forgot the left-hand side. The left-hand side is not correctly written. Maybe that is. Now, does it look more correct?
Yes, sir. Sir,
Now
I
it
guess
looks more correct.
yes, sir. Sir, I guess this can be
Okay,
easily
good.
if we write f in bracket notation. Means,
You do that. Why should
that
I
is
bother to? This is not quantum mechanics, my dear sir, Akshay.
But
So this is
the
true, right?
Fourier
Because this
transform
is
relations comes from there.
that's what this is, right? Now all we have to do is interchange I'm not going to write the integral twice, integral sign twice, but just this twice. But I will write this twice because of this. Okay, so now we have this fellow, that's simply a delta function. Sorry. Omega plus omega prime. You agree? This is simply omega plus omega prime. Okay, and this one then becomes d omega by 2 pi. D omega prime by 2 pi f tilde of omega, f tilde of omega prime delta omega, well, there's a 2 pi also. And now I can use the delta function to do the integral, right, over omega prime, let us say, and this becomes, so there's a 2 pi, this is always a 2 pi here, which cancels the 2 pi, so you can do the integral over omega prime, and what you get is integral d omega by 2 pi, right, f tilde omega, f tilde minus omega, because omega prime is equal to minus omega. That's where the delta function fires. And of course, f tilde star. So this is d omega by 2 pi mod okay, so that's the proof, 3 lines. This is no big deal really. The reason I was not getting the proof in the first place was because I wrote the formula wrong. So that's it. So that's proof. So now how do we use this? How do we use this? Okay. So we what we know is that we know that P of t can be written as, following the same kind of argument, that is just a Fourier transform, right? So this implies that P double dot, well, if you take a derivative with respect to time, that just brings down a minus I omega. So we can go straight to double dot, take 2 derivatives, and that is minus omega squared, right? Okay. And now what we're interested in, you see, is ERAD. ERAD, what was ERAD? Well, we have ERAD dt.
E to the power minus omega t will be there, right?
Oh, yeah. Sorry, to the minus I omega. Of course will be there. So we know what P double dot is. P double dot is just this. Now ERAD, remember, is integral. Okay, so let's recall that formula. So d ERAD dt was 2 by 3. Well, just go back to the previous page. Look, yeah, right here. So this one is d ERAD dt, right? Yeah, I will also give it here. So there's a square here, and we want to do is go start from here. So we go to the next page. So ERAD is integral q squared 2 by 3 q squared by c cubed dt squared, right? And we can write this as, so basically that's what we would like to have, but yeah. So we can now use straightforwardly, yes. So P double dot is this, right? So we can use directly Parseval's formula, okay? Parseval's formula can be directly used, okay? And what we have is 2q squared by 3c cubed integral d omega by 2 pi, okay? And we know what this is. So we have P So we will have this quantity squared, basically, mod squared of this quantity, right? That's what the formula says, that you must have, if you take the square of this and integrate over all time, then whatever Fourier, so this is e to the minus I omega t times this, so we'll just have this quantity. That's the answer by Parseval's theorem.
Sir, will there be a q square term here or not? I think it shouldn't be there.
Ah, you're right, ma'am. Oh, it's already included in the denominator in the dipole moment. You're absolutely right. Stupid of me. Sometimes this board is so infuriating because I can't do anything fast like I can do on a blackboard, you know. So 2 by 3c cubed, so this is a cube. Oof, this becomes terrible. A blackboard is so much easier to write. Okay, by Parseval. Okay, so E rad is given by this and also now given as an integral over omega. So we can now work out, answer our question, dE rad d omega is equal to, so what we get is 1 over 3 pi c cubed omega to the fourth. Okay? Oh, stupid. I mean small omega, of course. So the frequency distribution of the emitted radiation goes as omega to the power of 4 times the dipole moment Fourier transform mod squared of the dipole moment. Okay? So this is the frequency distribution. So we have derived using Parseval's formula, we've been able to derive in a very simple way the radiated intensity spectral distribution. What is the radiated intensity, radiated energy between frequency omega and omega plus d omega? So if you take the d omega that side, that's exactly the formula dE rad is equal to this quantity times d omega. So this is the radiated intensity distribution, spectral distribution. It's called the spectral distribution. Any questions on this spectral thing? So, good. So we have done more or less what I wanted to tell you about dipole radiation. I will do, yes, question? Yes, please.
That this is going to be might be a silly question. That is, this spectral distribution, has it got any analogy to the black body radiation? Because I see omega to the power 4 here, and in case of black body radiation, we have t to the power 4. So.
Yeah, you're very correct. Okay, so of course, the black body radiation has to do with radiation inside a cavity, of course. Here we have a radiation due to a point charge which is moving free. So the two situations are different because black body radiation, there will be the issue of volume. There's no volume factor here because the volume of entire space is infinity. Whereas in the case of black body radiation, of course, you'll have a cavity, so the volume of the cavity will be important and so on. And there, the other thing is, here, omega is continuous. Omega is continuous. Whereas in the black body radiation, because the fact that you have a cavity, only certain discrete frequencies are allowed. You've done black body radiation, I suppose, in thermodynamics, right? Aditya, you must have done it.
Yes, sir.
And you remember that this will not be a Fourier transform, but a Fourier series. But that brings us to an interesting question. So suppose we had a situation where the charge was not moving any which way it liked, but at a bounded motion. Like the charge could be going around in a circle. Okay? So that is not exactly black body radiation, but in that case, you see, you can ask the question, so if the charge goes around in a circle, the motion is periodic. Now, I think you know enough about Fourier transforms and Fourier series, okay, to tell me, so how much energy, how would the energy radiated per Fourier mode n depend on n in the case of, suppose the fundamental frequency was omega naught. So let me ask the question. It's a good question. Actually, Aditya has brought up a good question. It's not exactly black body radiation, Aditya, for reasons I said. But on the other hand, if you have bounded motion, like in a circle, let us say, or periodic motion, and we shall assume periodic motion of the charge, with frequency okay. And then I ask you the question, what is the energy radiated for the nth Fourier mode? How does it depend on omega naught and n? Forget the other constants, we won't worry about that. Well, we can, but how does it, let me just ask the question, how do you expect from what we did just now, how should En depend on n and omega naught? Anyone? Maybe Aditya also, can you answer this? No. Hello, can you hear me all? Can you hear me? Shomona. Yeah, Shomona. I like this picture of Hongsho Balaka. Very nice picture of Hongsho Balaka that you posted. So Shomona, can you tell me?
Sir, actually, I didn't get your question completely.
Yeah, my question is, if you have a charge executing bounded motion, like a periodic motion with a frequency omega naught, okay, I am asking about the energy radiated in the Fourier mode, the nth Fourier mode, En. Now, I'm assuming that you have had a course on Fourier series and things like that, periodic motion, Fourier analysis. Have you not done Fourier analysis? So given that the Fourier transform, given that if you had continuous frequencies, then the Fourier transform of the energy radiated goes as omega to the fourth times the mod of this quantity. Can you from here tell me what would be the nth Fourier mode energy? Can you tell me for bounded motion? I mean, you can do the calculation. You can, of course, calculate it exactly, but can you tell me without a calculation what it should be? You should be able to do this, right? That is why I ask these questions about intuition. So how does this go? You know, it is very simple. It is omega, it's proportional to omega n to the power of 4
So to
times,
n to the power 4 then.
yes, times the nth Fourier coefficient of the nth term, the Fourier coefficient squared. Okay, mod squared. We solve this. En squared. So that's what it is. And this is nothing but n to the fourth, omega 0 to the fourth, where Pn is the Fourier coefficient. see, P of omega and Pn are exactly the same. So if you work with discrete frequencies, that's what you get. Okay. Now this is a part of math which I thought was covered way back. So I'm expecting a response from all of you about this. It goes as n to the fourth, omega to the fourth. But I would now, what I'm going to do is set you an exercise in the assignment so that this thing becomes clear to all of you. So you have to work it out, the details. But intuitively, you know that if you have periodic motion, then this omega to the fourth dependence tells us that it's going to be omega n to the fourth dependence, which goes like this. Is that clear? Hello? Class?
Yes, sir.
Is that clear? Okay, good, good. But unfortunately, I will not be doing black body radiation. But then you can see from here the other aspect. Sorry, why am I going here? In this case, also, this omega to the fourth dependence means that as omega goes higher and higher, the energy radiated keeps going higher and higher. Okay. This omega fourth dependence also goes by the name of Rayleigh's formula. And Rayleigh's formula, okay, was used by Rayleigh and Jeans exactly to work out the radiation spectrum in a cavity for black body, a black body cavity. That's exactly what they did. And the same formula told them that the energy goes up and up. And that is why you have what in black body radiation is called the ultraviolet catastrophe, which then prompted Max Planck to suggest his fantastic quantization rule, right? That you have oscillators without a continuum of energies, where the energies are always in quanta, okay, of some basic quanta h bar omega. Anyway, so that's the connection, okay. So at least, oops, yeah. So here we are. So I still have 7 more minutes. So in the meantime, what I'm going to do, okay, so is there any other question about this non-relativistic approximation? Because I'm going to quit now. I'm going to come back to it when we do multiple radiation, that'll be a little later. What I'm going to do now is go back to relativistic formula, relativistic charge. So some issues have come up, and while I will try to give you another homework set, but there is already a homework set at your disposal, but some of these issues I think you should discuss with Orithro as well and amongst each other. So do come for the tutorial. This week's tutorial I will not be taking. Well, I'm wondering whether I should take it or not, but maybe I shouldn't. Let me for this week, maybe next week's tutorial I will take because I will be very out of time. But this week's tutorial I will not take. Now for a relativistic charge in external EM fields. So now we want to go to a situation, right, where we would talk about a relativistic point charge, however, whose motion is being dictated by external electromagnetic fields, which I shall call F bar. So the bar simply indicates that we are dealing with a charge which is in this external electromagnetic field. So this is, of course, this will be, in components, this will be E bar and B bar. So today I don't have time perhaps to solve the problem, but we know what the motion of the particle is, of course, given by the relativistic Lorentz force, which is this. This you've all seen, right? But then we have a little problem. If we want to talk about the intensity, okay, how do we do this? Now, we were able to solve for the intensity explicitly by integrating over angles in the non-relativistic case. Now, what we know is that, well, so from here, what we get is a formula for the acceleration. If the mass of the charge, if the mass of the charge is m, then this is nothing but q by mc. So that's the acceleration. But what good does that do? Because you see, what we know in case of radiation from a point charge is this formula. Our favorite formula was this. A squared, oh, r dot u whole squared plus u squared okay, that's what we have. Now, what we want from here is basically P radiation, okay, let's say B. We want the 4 momentum, and from there we know what the energy is. V equal to 0 is the energy. So this is minus Q squared 4 pi C R0 well, let me not write this whole thing down again. Well, I have to write this down, but P rad basically is a space integral. Okay, of this quantity T 0B rad. The question is, how do we calculate it? Okay, how do we calculate this quantity? Now, this is a very non-trivial question, and it's not answered, believe you, in any of the textbooks. But what they do is something crazy. Well, it's not crazy, it's perhaps the right thing to do. See, they extrapolate textbooks. Extrapolate from Larmor's formula. So you have the formula for the intensity, for the energy, radiated energy, in the non-relativistic domain. Now write down a formula, okay? So write down dP rad P in such a way that it agrees minus 2 by 3 Q squared by C fifth, I think, times A squared UB theta. Okay, and I think this formula is right. So the question is to check. So A squared is the full acceleration, right? And this is UB. So UB. So basically, the check if P equal to 0, non-relativistic limit gives back Larmor. Okay, so that's the kind of thing I think. I'm always very non-confident about. Yeah, I think this is right. I think this is correct. So this, you should be able to do this calculation. If not, you have to make the corrections here with the C and so on. Everything else is okay. A squared, remember, A squared is basically minus A non-relativistic squared. So that should work out. And A non-relativistic squared is beta dot squared times C squared. So that should give you the right formula. But I'm not 100% about the C factor. Is this a C cubed? Hang on. Let me just check. Yeah, I think it's a CQ. That's right. It's a CQ, not a 50. Oh boy. So I think this is a CQ. But check, okay? Now what we can do, is if this formula, okay, so I'll do two things. Today I'm out of time. So in the next class, what we'll do is, let me just mention it. Let me mention for what it's worth. You see, this formula was pulled out of the hat. Completely out of the hat, and then you just argue that, well, this gives the right limit, so what else can it be? But it is always a difficult task to extrapolate from a non-relativistic result to what the correct relativistic result is. Because, you can have other expressions also which lead to the same limit. There may be several things which lead to the same limit. So there is a huge ambiguity if you say that, well, this is a good candidate formula. It's also probably physically relevant, but I don't have a derivation. I need a derivation from here by doing the integral. And would you believe it, that this integral was done at the cultivation of science and at presidency. So we wrote a paper. So the authors of this paper are Anaria Ray from Presidency. He's now abroad doing his PhD in Wisconsin, Milwaukee. And then Zahid Ansari. Who was a student just like you guys. And he and I and Anaria worked together, and of course, yours truly. In 2018, we have this paper. You can check it on the net. I'll give you the paper also. I'll send you the paper. It's a little difficult. The paper is, written for, it's not published yet because the journal has died. So I have to find another journal. The journal went out of business during COVID. So I have to find another journal. Canadian Journal of Physics, it just, refused to answer. So it's probably some COVID thing. But there's a paper. It's on the archives. So I can't remember the archive number, but I'll send you the paper. I have the paper. I'll send it to all of you. But we have worked this out. We have done this integral. Okay, exactly, without approximations. So this integral is done, and you get a formula which is exactly this. So this formula is correct. But the point is that we have been able to give the derivation. It's one of the other things that is not given in any textbook. This derivation is not given in any textbook. And yet, this will be the most, if physics is not done by smart guesses alone, you also have to provide proofs. And the proof has been provided by the three of us. Okay? So this is a paper which was written in the electrodynamics class, to be honest. And it was worked out together. And that class, Zahid, unfortunately, was not absorbed by ISCS as a research student. And that reason for that was never clear to me, because he was definitely a fantastic student. Zahid is now in Tata Institute of Fundamental Research. Anari, of course, never applied here. He went straight abroad. He's now working on gravitational waves. Zahid is doing, I think, dark matter cosmology with Amol Dighe. Yeah, I think he's working with Amol Dighe in Tata Institute. So they're doing very well, but they did work with me, and I'm very proud that I had such good students working with me. So, but the other point is to show that even inside a class, in as old a topic as electrodynamics, there are issues on which you can write a paper. You just have to be courageous and work very, very hard, because you can see from the paper that it's not a trivial calculation. Okay, so much for today. Sorry for taking a little bit of your extra time, and we shall meet again on Thursday. Bye-bye.